Okay, so welcome everybody to the December meeting of the Morton-Finnish Astronomical Society, the first official face-to-face monthly meeting we've had since the lockdowns occurred. We have actually been here for other reasons, but not for the general meeting. Quite a lot has actually occurred in the last month. Normally we don't hold a December meeting of the Society, but we did this year because it's been an unusual year, so we thought we'd do something unusual and have a December meeting as well. Lots of things have actually happened in the astronomical world as well, and you see a couple of the pictures up there. One by the Arecibo radio telescope observatory in Puerto Rico, and we'll show a little bit more about that in a few moments. That of course is a dish that is over 300 metres diameter, so you're getting on for about 2 football fields in size along its diameter axis, and unfortunately it collapsed earlier in the month, and we'll see that happen in a moment. Also, the Japanese spacecraft that visited asteroid called Ryugu, a near-Earth asteroid, came back as a close pass to the Earth and dropped its sample return capsule, which you may have seen on the news, parachuted successfully down in Woomera, and I'll show you a bit more about that a little bit later on. What's shown there is the image that it took, composite image, sort of rotating round and round as a GIF from when it was close by to that particular asteroid. That one is about 50% space in it, so it's like a collection of loose gravel, so it's not a solid lump of rock, so appearances can be deceptive. Also, the size of that asteroid is over twice as large as the Arecibo telescope there, to put it into context. So you need to sort of at least double it and maybe a bit more of the Arecibo to get the true size of that rock. Certainly not something that you want landing on you.
You've got any idea how fast that's rotating?
I think it's about 7 hours, I think, of that order.
Per rotation?
Yeah, so it's relatively slow. But yeah, quite normal and approximates a sphere, a bit of a cupcake or a diamond shape, they call it in the media. And with the Arecibo telescope, when we get to that, that's actually formed in a natural sinkhole. So when they actually built it, they put it in a sinkhole, and the vegetation underneath it obviously has to be shade tolerant, given that it doesn't get to see much light under there. And who knows what's going to happen with that particular one. Now down the bottom also, you may or may not have seen, depending on the news service that you watched, there was a total solar eclipse a couple of days ago that passed over South America, and you can see the NASA predicted path in sort of pinky purpley down the bottom there. Went across Chile on the western side, the left side of South America, and then was seen a couple of minutes later on the right-hand side, the eastern side with Argentina. Maximum duration of it was only about 2 minutes and 10 seconds, but I'll show a video of that afterwards that was recorded live at the time. So quite a bit has actually happened. So tonight, welcome anyone who's never been to one of these meetings before. If you're new to the Society, or maybe you're not new and this is just the first time you've come along, just try and hunt up our new members officer, who will now put her hand in the air. That's Nerida at the back there, quietly putting her hand up. Also a reminder to members who haven't renewed yet for next year that the renewal date is 1st of January every year. There will be a mail-out reminder goes out soon to give you a prompt to renew if you haven't. If you've only just recently joined the Society as a brand new member, you don't need to renew, because you would have been given the remainder of 2020 for free as part of joining in the closing parts of the year. I'll go through the Arecibo observatory collapse and show you the footage of that, and show you also beforehand the actual size of it. You don't really grasp it until you see it relative to a person climbing along the gangway. And I'll sort of show you a before and after. go through the events of the past and the upcoming month or two. Then Ross Berner, who's a member of the Society as well for a while, and certainly a long-term ASV member, will give a talk about Supernovae. That's where we'll juggle cables and see what the technology does to us there. Then following that, the Sky for the Month by Mark Stevens at the back there. Sky Murphy's not here tonight, but she sent hers in as a video, so we'll show that, and it's all about the number 12, which is quite intriguing. Then after that, we'll go to a series of smaller videos of about between 5 and 10 minutes each. One is the actual Hyabusa 2 capsule return. Compiled a number of those from different sources to sort of show. We'll then look at the Elon Musk's SpaceX attempt at launching its Starship first flight. I'll show you the entire flight, which lasted for about 8 minutes between takeoff and unscheduled rapid disassembly, I think was what Elon Musk referred to it as it landed. And on the positive side, when it landed, it actually did land middle of the pad. Just didn't land entirely as anticipated. After that, we'll actually show you the solar eclipse footage from Chile and then Argentina as well, as was transmitted online at the time by the so-called virtual telescope. Then lastly, we'll ask the question of why is glass transparent? Why can you see through glass but not through other solids? Now, glass is ubiquitous around every telescope that you have, all the optics and everything. Yet, why does it actually let through light, and why does it let through certain colours of light? And this is an interesting explanation which explains it quite well by a physicist from Nottingham University. Then, to close the meeting at the end, this month we'll have a guest musical director, Diana Clark from the Cadence Choir in Black Rock. Will be put behind a video that shows the entire birth of the universe up to today from the Open Mind website as well. So quite interesting having both of those together. So let's begin first of all with the Arecibo observatory collapse that occurred on the 1st of December. It had had a couple of near misses since August when it had some malfunctions, and the worst one in November, which I think we reported in the last meeting that we had, came pretty close to being the end of it then, and it was only a matter of time as to whether it failed itself or whether it had to be demolished very, very carefully, and that would have been a very dangerous task to have done. So what this first clip is, when it wakes up, is for about a minute or two, it will be silent, and this is like the before image of Arecibo, and you get an idea of the scale of it. So you see in the middle here, you have this triangular shaped receiver. Now that weighs about 900 tonnes, suspended from those cables. And obviously you don't want one of those cables to break, otherwise it turns into a very large pendulum very, very quickly. And in a moment you'll see how astronomers and the engineers there move across to the centre. Now there's a gangway that joins it, and you can see it on the right here, and here's one astronomer moving across the gangway towards the centre of the receiver above the telescope. And in a moment when they pan out, you'll see the size of what he's walking on that triangular bit is absolutely large, is enormous. And you don't sort of appreciate it when you get like a drone's eye view from a long way away. It is very, very big indeed. And that's the view looking upwards from the gangway. And this, of course, is all before. And you'd be pretty lucky to be the last person to have successfully gone across that before the thing started to get a bit dodgy. Fortunately, no one was injured. They restricted access and decided to go the decommissioning route after the November failure. But it was quite a failure that occurred on the 1st of December. 1st of December, our time, we were about 15 hours, I think, ahead of Peurto Rico. So for us, it would have been getting off about 10:30 at night when this occurred. Now you'll see the live footage taken, one from the control tower, looking, and another one from a drone. A sad rumble in the jungle for that one. Now you'll see the drone footage. Steel cables that were holding it up were about 3¼ inches diameter. So they certainly were designed to be able to take the weight of it without any problems at all, and a certain degree of failure. But obviously, too many of those individual strands failed, and you could indeed hear the pinging, right, as each of them individually failed, which is pretty typical when a steel cable gets pretty close to the breaking point. And as you might have seen, it just sliced through the surface of the dish, which is just aluminium plate with little or no resistance at all.
Back in August, Peter, were the strands actually failing then, or was that November the first strands actually went?
The August one, they thought it was actually the connection point. So in other words, it was a manufacturing fault. So it wasn't actually a cable failure at that particular time, but it should have been able to survive that anyway, because they had designed a certain safety margin.
It certainly caused the cable to go, didn't it?
Yeah. Yeah. Now the thing is, the Arecibo telescope has been hit by hurricanes, what we call cyclones in our hemisphere. It's also had earthquakes, and I believe they said that a recent earthquake was thought to have been an underlying trigger for this particular event. So it didn't sort of come out of the blue after a major storm had gone through or anything like that, but they did mention that it was an earthquake as the likely cause.
There was also some corrosion there too, wasn't there?
Yeah, well, given it was, I think, about 57 years old, yes. You might expect a little bit of metal fatigue over that style, a little bit of corrosion. Ordinarily, metal fatigue will occur with metal that's continually bending, like the wings of an aircraft or that. And you'd like to think that that wasn't flexing too much in the wing, given that it was subsided in a sinkhole, a natural sinkhole in Peurto Rico. Yeah, Fred.
Wouldn't they have had with a thing like that collapsing? Wouldn't there been a board of inquiry into exactly what had happened? Because people could have got killed there.
Well, if it had occurred suddenly and without any prior notice, people could easily have been killed. Yeah.
Was this a very, very old place in the foundation?
It was about 57 years since they started it, and it was a case, I think, of the maintenance couldn't be done because there wasn't the funding to do it. So they sort of cut corners and put maintenance schedules off. And you see what happens. Aeroplanes drop from skies and radio telescopes collapse. That was 1st of December, so not long ago, right? Just a couple of weeks ago.
Up to how recently was it operational?
Well, 57 years was how it's been operating.
But up until when would it have last been?
Oh, I think they made the decision to kill it in when when was that in November? I think it was just a day before our last meeting, so middle of November.
Collecting data up until then.
Yeah, and up to that point, that was it. Right. So that's the use of the telescope itself. I think there's like a visitor centre there and a smaller telescope on site as well that they can use for some sort of interferometry.
There is another instrument there.
Yeah,
I don't know what that is, so.
And I think that one is still operating perfectly
operating.
fine.
Was this in America, Peter, was it?
Puerto Rico, so strictly speaking, it's American territory. Yes. Yeah. So it's on the right-hand side of where North America joins South America. One of the islands there.
You haven't heard anything along the lines of vibrations and frequencies due to perhaps the cyclone or any of those?
No, I haven't heard about that. Whether it's reached a natural harmonic frequency or something, whether that has occurred. No, I don't know. I'm sure someone will look at that as maybe a thesis or something to see why this particular thing failed. Maybe a mechanical engineering thesis done on that one. Okay, society events recently. Obviously this year we're not doing any public scout or any other outreach nights, but they all start kicking in as of the 2nd of January. In November, in fact at the time of this meeting last month, we had the first of our presenter training done here at the Briars, and then the second was done a couple of weeks later on the 9th of December here. So we have actually had meetings here for specific numbers of people to actually train them how to be a presenter at public nights, for example. And of course we were limited to far fewer numbers than are seated in here today for those ones. On the 25th of November we had a committee meeting and we had our annual fire inspection, which we passed without too many issues at all. Did a bit of polishing on the COVID safe plan for here at the Briars, because you have to have a COVID safe plan for every location where you are. So for example, when we do viewing nights or even members meetings here, you have to have a COVID safe plan. If you do a night at a school, you have to have a COVID safe plan. So that's one of the rules that the government has in place. We also looked at the logistics of the Christmas dinner and talked a bit about pest-proofing the toilets by dropping the roof down to take away the need for the mesh there. And we looked at the final calendar updates and the updates to go out with a reminder about the annual fees reminder. 5th of December, we had some members here at the Briars. I wasn't actually there that Saturday, but there was a working bee also last Saturday to get the telescopes up and aligned. I think they're all aligned now. Yeah, not quite. Okay, all right, maybe aligned, maybe not. And of course, tonight being a special night, we don't normally have the December meeting. Now, coming up on the foreseeable future, we have the annual Christmas dinner, which is going to be held here on this Saturday. If you haven't booked, I don't know if there's any places left. Does anyone know? That's back? No, it's closed. Closed down. So we are at maximum holding capacity for the society under the current regulations for that one. And that one was a $10 booking fee, but you'll get that reimbursed to you when you turn up on Saturday. So if it's a no-show, you lose your money. If you do show, it actually costs you nothing. So pretty good deal.
And you get a dinner.
And you get a dinner, yeah. On the 21st of December, which is Monday, from about sunset onwards, we'll be at the base of Oliver's Hill with telescopes. So we're likely to get the public wandering by, I would think, for that, and we'll ask for just a gold coin donation if people have the inclination to do so, or we'll show it to them for free if they haven't got any money on them. But we'll be at the base of Oliver's Hill. Any members are welcome to obviously come along and bring your own telescopes as well. One of the requirements COVID safe-wise for looking through your telescopes will be anyone who wishes to look through it will look through a piece of glad wrap. So in other words, they'll put a bit, their own bit of glad wrap over the eyepiece and take it with them afterwards. So in other words, people will not be touching the telescopes at all. They'll be given a bit of glad wrap, and that's what they take from one to the other. So pretty bizarre. I believe it has been tested here on one of the earlier nights by Guido, who's not here, and it works perfectly fine. Perfectly fine. We'll have the amazing properties of Woomera. Public stargazing nights will start on the Saturday, 2nd of January. Normally we hold them on the Fridays, but as you see, Friday's the 1st of January, and we may not get too many people here on that night after they're recovering from a late night the night before. So the committee decided to make the first public night back here on the Saturday, 8 o'clock as normal times that we hold those, and then succeeding Fridays after that, so on the 8th of January, 15th and the 22nd as well. We're back here on the 20th of January for the January meeting of the Society, and we've already got school nights that have booked in already for March, so the schools are back, whereas up to now schools have definitely shut down all excursions anyway, so we weren't going to get into any of those, and any that we had already booked were obviously cancelled during the lockdown period. We're also into the hobby exhibition, which we haven't been to that show before, that goes for 3 days in March, so we'll be looking for members to man a table over that period of time, or stand by a table, and I think Dave Roll put a message out on these Scorpius about that one. So if you can help closer to the day, put your hand up and we'll sort of slot the time.
This is one at Sandown.
Sorry?
This one at Sandown.
Yes, I think so, yes. Yeah.
It is the Sandown.
Yeah. The dinosaur exhibition, the fossil thing at Point Leo, our guide has now confirmed that it's going to be on the 21st of March, which is a Sunday. That's the one that was originally last November, but we couldn't have it because of the restriction on meetings. So hopefully by the 21st of March we'll have no issue with even a large group of people being able to tag along for that particular one. Right, now before I will go into the other ones, like looking at the Ryugu probe after the talk a little bit later, but we'll go into the main talk tonight from Ross. Ross has been in the Society several years now. He's a long-term member of the ASV, and he is the section director there of their cosmology and astrophysics section, so he knows a lot about this topic. His background, he tells me, is electrical engineering as well, so he knows a bit about that as well. And hopefully the technology will work okay for you, Ross.
Okay. Okay, so the breaking the talk up into sections. The importance of supernova is the first part. We'll look a little bit at what happens with stars forming elements and how it relates to supernova. We'll look at type 2 supernova, several other types, type 1A, and then other types. There's some very interesting ones that have been recently discovered. So, importance of supernova. So, start off with the early universe. We've only got hydrogen and helium in it. Not really. And with gravitation causes that to form stars. So you get the protostar, and they're all, the original stars are all very big. They form blue giants, red supergiants, and they go bang with supernova, form planetary nebula. And the planetary nebula gets mixed in with the rest of the hydrogen and helium in the universe, and forms more protostars. Okay. So, as I said, the hydrogen and helium initially was the only thing that was created. There was a little bit of lithium, but that was parts per billion, so it was really not relevant. Everything else that you and I are made of, and everything around us, has been created in the core of large stars. There would be no carbon, no oxygen, nitrogen, iron, any of those without supernova. Okay, so the first stars we call population 3 stars. When they started numbering them, they started with the closest stars, which are population 1. Population 3 stars probably should be called first generation stars, but So, and supernova, when a supernova explodes, it pushes heavy elements out in what's called a planetary nebula, and that gets mixed into the surrounding elements, and they mix with hydrogen, aiding further star formation. So you see that same diagram again. This is the astrophysics periodic table. Basically, as far as astrophysicists are concerned, there are three elements: hydrogen, helium, and everything else. And this is, with apologies to Professor John Latanzi, who I pinched it off. Okay, so when stars form, the first thing they do is they start to convert hydrogen into helium, and these are the reactions that happen. So you start off at the top here. So you've got two hydrogen. They combine, and that forms deuterium, which is another form of hydrogen, but it's got a proton and a neutron. Deuterium is stable. This reaction actually is one of the most important reactions in the universe. It provides more than half all the entire energy in the entire universe. All the other subsequent reactions all produce less than all the other combined produce less than what's produced by this first reaction. Then another proton gets added. This one here gets added to an existing deuterium, forms helium-3, and finally two heliums collide, form helium-4, and it gives off two protons which go on and react further. So that happened in the Big Bang to form the helium. It also happens within stars. Every star is unless it's burned all its hydrogen, is doing that reaction somewhere in the star. Okay, so within a star, you've got self-gravitation. So you know the weight of the gas in the star is pressing down, trying to make it smaller, and the radiation pressure from the core where the fusion is occurring is acting to expand the star. And the behaviour of the star can be explained by the balance of those two forces. So the fusion reduces, the star will contract in size, it'll heat up, fusion increases, star gets bigger. Okay, so most of the stars in the sky, you've probably all seen this diagram, the HR diagram. Most of the stars lie on this what they call the main sequence, which comes through here. So these are red dwarfs. Right about here's our sun. You're just here. It's our sun, often called the yellow dwarf. You get up to here, and these larger stars up here are blue giants and supergiants, and these are the ones really we're talking about. These are the ones that go supernova. When they finish burning their when they reduce the amount of hydrogen in the core, they'll form these red supergiants, and these are the first stage before going supernova. Whereas smaller stars will produce white dwarfs, which are effectively dead. Okay, so when it starts running out of hydrogen, the core cools, causing it to compress and raise the temperature. And one of the first things that happen is that helium then starts burning and forms carbon. Stars move off the main sequence to form red supergiants. Hydrogen burning continues outside the core, and we start seeing this layered effect, which becomes more predominant later on. Carbon is produced in what's called the triple alpha reaction. So two helium collide and form beryllium-8. Beryllium-8 is very unstable. It's got a half-life of about a nanosecond. And a lot of people wondered how helium got to carbon, but it was found that if in the core there's a lot of helium there, the rate of collision is very high, and if a third helium hits the beryllium, this third helium over here hits the beryllium before it decays, more often than not it will produce a carbon-12. And carbon-12 is quite stable, so it's just purely weight of reaction. So obviously the hotter and denser it is, the more likely the reaction goes ahead. Yeah, so helium is extremely stable, but as I said, if the temperature and the pressure are high enough, it will proceed. Okay, smaller stars such as our Sun do not proceed past producing carbon. When helium is depleted, they shed their outer layers as a planetary nebula, form a white dwarf, which is no longer an active star. So essentially, unless something else happens, they're effectively just cool and eventually become what they call a black dwarf. But I believe there are no black dwarfs yet. There's not enough time in the universe yet to create them. White dwarfs are quite hot because they're very compressed, but they're not doing anything. Just cooling down. Okay, so once you start getting a lot of carbon in the core, it starts to go through another cycle. It compresses and expands again. It starts to produce what's called the CNO cycle, and in this one here, it absorbs hydrogen or protons, and it gives off electrons and so forth, and it forms nitrogen and oxygen in this cycle. This is one of the cycles that occurs. Yeah, so it involves proton capture and beta decay, and beta decay, it's giving off a positron, which is an anti-electron. And as particularly for very large stars, as the next sort of process on is really to build up to bigger and bigger elements. And so we start here with carbon-12. If we add a helium, we get to oxygen, neon, magnesium, silicon, sulfur, argon, and so on, up to nickel. Okay, and you'll notice here there are some side reactions that occur, but these are relatively minor. These are changing by emitting a positron, positron which turns a proton into a neutron. Okay, so we start to see sort of this onion-like shape developing, and with this, what's happening is you've got a variety of different reactions happening in each of these layers, and the temperature and the pressure is getting hotter and hotter as you go in towards the middle. You've generally still got a lot of hydrogen fusion on the outside, helium fusion, carbon fusion, oxygen. So all the different earlier reactions are still happening in the outer layers where the temperature is lower and the pressure is lower. But in the middle, you're building up to form iron and nickel. And even the outer layers often not hot enough to even burn hydrogen. Okay, so these are some of the reactions. As well as adding helium to things, there's also some other reactions that occur. For example, two carbons can combine to form a neon and a helium. The neon will form oxygen. 2 oxygens will form a silicon, and then we get to silicon fusion, and from there on it basically just adds helium. It goes up in steps by helium until nickel 56 is produced. And nickel 56 is the end of the process. So these are the reactions there. Nickel 56 basically is one of a few elements that have the highest bonding energy. So if you add anything to it, it will absorb energy and it will basically put the fire out. So the reaction no longer gives off any energy, and that basically causes the death of the star. Okay. Protons and neutrons are an atomic nucleus arranged in shells. This, I believe, is an oxygen 16. I sort of counted everything up, and I reckon this is 8 of each. So there's basically 4 in the middle, and then forming the inner shell, which is essentially a helium, and then there's another 6 on the next layer out. Now, in the same way the periodic table represents filled shells of electrons, you get filled shells within the nucleus. And there are so-called magic numbers, 2, 8, 20, 28, 50, 82 and 126. Double magic is where you've got a magic number of both, and notably you've got helium, oxygen 16, calcium 40, calcium 48, which is pretty rare, nickel 56, and lead 208. All those ones I've listed above there are stable except for nickel 56. Okay, so up until calcium 40, nuclei prefer equal numbers of protons and neutrons. What happens is, once you get past that shell of the third shell, when you get into the fourth shell, the strong nuclear force is no longer attracting every proton and neutron to each other. So the strong nuclear force is limited in size to about the diameter of a calcium nucleus. There's still some strength there, but it falls away very quickly. And this is one of the things that leads to iron and nickel being at the top of this bonding energy. Once you get past that, the repulsions build up. So the strong force only acts between the closest protons and neutrons. It doesn't bond across the whole nucleus for big nuclei. Protons in the outer shells are held weakly. Extra neutrons are needed to be stable. The neutrons don't repel each other, whereas the protons do. The protons repel because of the electromagnetic force, but the neutrons are essentially stable, essentially neutral. Okay, when nickel 56 is produced, no energy is produced, which causes the core to collapse. And the day nickel 56 is produced, that's the day the star goes up. Basically, less than 24 hours after it's produced, the star goes up. Now, a lot of books talk about iron 56 being produced in the supernova, but that's not strictly correct, and I'll explain that in a minute. The inner core is compressed to form neutrons with the density of a nucleus. It generates enormous heat, and the outer layers initially collapse onto the core, then rebound violently, blowing the star apart. So basically, you can see there, the first sort of 2 pictures there are sort of showing things collapsing in. So initially, the core itself collapses in. Then the outer layers collapse in, and then you get the rebound, and it literally blows. But it results in this. Oops. Yeah, so it forms this, and this is basically represents the planetary nebula that gets blown off. Okay, the core becomes a remnant and the retaining material expands, producing the planetary nebula, and that's the Crab Nebula, I believe. If my sources were correct. The stars have 10 to 20 solar masses. The remnant is a neutron star. Larger than that, up to about 150 solar masses, to black hole. Type 2 basically go up to 150 solar masses. And in the process that this blowing apart, it actually creates a massive atomic reaction, and that produces a lot of large elements. It does it by a variety of processes. It does it by alpha chain, which is adding helium. It does it by neutron capture and beta decay. So the process only goes for a limited amount of time, but it does create quite a lot of different elements in the process. Okay. All right. So Type 2 supernova occur with population 2 stars and population 1 stars. And these are what's called low metallicity stars and high metallicity stars. And metallicity basically is defined as the total mass of everything except the hydrogen and the helium over the total mass of everything, which is a pretty hard number to work for researchers to work out if you look at a distant star. So what they tend to do is they tend to look at the ratio of oxygen to hydrogen and iron to hydrogen, and that gives them a good clue as to where that lies on the metallicity scale. So population 2 stars, I generally prefer to call them second generation, population 1, third generation stars. Now, nickel 56 is unstable. As I said, once you get to that fourth layer, the outer protons are repelling each other. And nickel 56 has a half-life of 6.1 days. It decays to cobalt 56 and then in about a month's time to iron 56. So the iron 56 we see well, we see everywhere. I mean, Lang will make a fortune off it, didn't he? The iron 56 basically is coming from nickel 56, which is decayed, and what's happening is one of the protons in the outer shell is decaying and forming a neutron. In fact, 2 of them are to get to iron. Nickel 56 can be seen in the spectra of supernova for around a month. So in other words, for about 4 half-lives. Okay, as we said before, these elements get spread across the thing and get drawn into subsequent star formation. Okay. Now, one of the questions I like to ask people who are really experts in it, I'm only a sort of an interpreter, if you like, or a secondary presenter, but someone who really studies these things, is how many times around the loop does it take to get to Earth, or to get to the Sun, I should say? And most of them say we're in the third cycle. But I did ask one guy once, and he said 100 times. Oh, that surprised me. Yeah, I sort of wonder whether, in fact, everyone's just saying 3 times around is a bit of a cop out, but it's my view on that. certainly, I would think maybe 3, 4, or 5 times, but I can't really think there's enough time to get it go 100 times around the loop. Okay, so there's 7 different types of type 2 supernova, and they all undergo basically the same core collapse. The difference between them relates to how big the star is, how bright it is, and how much metals it's got in, and so forth. And there really is no point in sort of going into that level of detail. If you want to go into that, there's plenty plenty of stuff on there. There's also type 1b and type 1c. Now, the difference between type 2 and type 1 is type 2 have hydrogen have hydrogen in their outer layers. Type 1 was noted for not having hydrogen. Now, type 1a is completely separate from type 1b and type 1c. Type 1b hang on, I've jumped a bit, sorry. So large stars can undergo shedding in their outer layers. Notable examples of shedding are Rita Carino and Betelgeuse. And this time, in fact, generally this year, one of the big puzzles was what was happening with Betelgeuse. And the explanation that they've come up with is that there was a very large outgassing that was heading in the direction of Earth. Now, it's never going to get here, it's only going to go a short distance. But you can see there's the first signs of the outgassing there, then you can see there it's actually gone away from the thing. As it goes away, it cools and forms this large cloud in front of Betelgeuse, and that had the effect of dropping the apparent magnitude of Betelgeuse by about a magnitude and a half. That cloud has now since dissipated a little bit, spread out, and it's not having much effect on the outer layers. But the important thing is that the outer layers of very large stars, typically up, and these can be 50 solar masses up to 150 solar masses, these will often get rid of the hydrogen from their outer layers in the process of this shedding. So a star which has shed all its hydrogen, it will undergo core collapse, similar to type 1, and it's called a type 1b supernova because there's no hydrogen, there's very little hydrogen showing in its light curve. And a star which has shed its hydrogen, both the layers, the hydrogen and the helium layers, is a type 1c supernova. I think these are relatively rare, but it's worth noting. Stars smaller than 10 solar masses never undergo core collapse. In about 10 billion years, our sun is expected. Our sun will become a red giant in about 4 billion years, and it'll start doing that triple in the core. It'll start doing that triple alpha process. But when the core becomes depleted of helium, all nuclear action stops and it collapses to become a white dwarf and sheds its outer layer to planetary nebula. And our sun, once it becomes a white dwarf, basically won't do anything. It'll just sit there and cool and eventually become a black dwarf. Initially, it's very, very hot. Okay, this is interesting. These are some of the densities. So, water, for example, has a density of 1,000. Osmium, which is apparently one of the heaviest metals, is a density of 22,600. The core of the sun, 150,000. A white dwarf is a billion, has a density of 1 billion. So so when the sun goes to a white dwarf, it's actually going to increase its density by about 4 orders of magnitude. I guess that's a sign of the strength that this nuclear fusion is pushing the outer layers out. But atomic nuclei is in the order of 10 to the 17. A neutron star, again around the order of 10 to the 17. And a black hole has got a density in the order of 10 to the 30, depending on the size, of course. So you can see that even the difference between a neutron star and a black hole is an enormous difference in density. But the highest theoretical density in the universe is Planck density, which is 10 to the 96. which makes one wonders what's actually inside a black hole. But anyway, that's another story. Okay, this is a photograph of Sirius A and B. And Sirius B with the arrow is a white dwarf, which is going around the blue giant. But 60% of star systems apparently contain 2 or more stars. In a binary system, if the largest star becomes a white dwarf, so we said white dwarfs don't do anything, but if it's a white dwarf of somewhere around about 1 solar mass, and it's in a binary system, and the smaller star is a red giant, so it's probably going to be 0.6, 0.8 solar masses maybe, whatever. Doesn't really matter what the numbers are. Then the white dwarf can, particularly if they're a close pair, the white dwarf can pull material off the red giant. You've probably seen this diagram, this sort of diagram before. So there's the red giant is on the left there. It's a bloated star. Red giants tend to be very diffuse in their outer layers. Very easy to pull material off. That material will come down onto an accretion disk, and friction within that disk will cause that material to fall onto the white dwarf, and it will build up the mass of the star. And if it gets to 1.44 solar masses or thereabouts, it will form a neutron star. Form a type 1 supernova, forming a neutron star. So this is a quite different process to the type 2, and for that matter, the type 1b and the type 1c. Novas actually can also occur by similar process. The difference there is the white dwarf is not destroyed. So in other words, you can get a situation where you get material drawn onto an accretion disk. Some of that, quite a bit of that material falls onto the white dwarf, causes a bit of a flare-up. It can actually cause it to actually start to reignite slightly. You get a nova, but then it quietens down again and cools off and goes back to being a white dwarf. But if it doesn't get to 1.44 solar masses, then it will go back to being a nice quiet white dwarf again. But if it gets to that 1.44 or pretty close to that, then it's going to collapse to form a neutron star. Type 1A supernova are used as a standard candle, and this was used to predict the existence of dark energy. Because obviously parallax only gets you a little bit out into the universe, and then you can look at other variable stars to get a little bit further. But you need something really, really bright like a supernova to do it. But because this primary method of type 1A supernova occurs at the same mass each time, then it does tend to produce a very uniform curve. There are some slight differences that needs to be taken into account, but you do get of all the type 1A supernova that occur, you do get a good number that are quite predictable in their behaviour. And of course, we know that our mate Brian, what's his name, got his Nobel Prize from Brian Schmidt. Got his Nobel Prize from this work on looking at the type 1A supernova, along with some of his colleagues and competitors. Type 1A supernova can also occur when 2 white dwarfs in a binary white dwarf system collide. In that case, where that occurs, they won't give off the same characteristic because the mass may be more than likely be heavier than 1.44 solar masses. Okay, other types. Electron capture supernova. Now, this is this is a small group that occur generally with 8 or 9 solar mass stars. They never get up to producing nickel in the core, but collapse with oxygen, neon and magnesium in the core. It behaves fairly similar to a typical type 2. I don't know whether this has actually got a type number, to be honest. I haven't seen one for it, but it's fairly small group of supernova in that one. Some of the other types, failed supernova. Close to the upper mass limit of a core collapse supernova, what happens is the collapse almost becomes an avalanche, and the material falling in doesn't rebound. And what actually happens is everything falls into a black hole and the star completely disappears. Keep in mind, I'll say with these other types, most of these there's only a few examples, whereas type 2, they're happening all the time, type 1A are happening all the time, and there's lots and lots of examples. With these other types, many of them only been recently identified. Many of them occur at quite large distances from us. So there have been a couple of examples where there's been what appears to be a supernova, no planetary nebula is created. Basically, the whole thing goes black, and when they've looked back, they've been able to work out where it's come from. They looked back, and they've seen that there was a big red supergiant there before it happened, and it's disappeared. And I really can't see anything because the black hole really is not producing enough not producing anything to send to them. So they just basically see nothing there. This type begins with a weak signal which fades and disappears, basically. A faint infrared signal is all that remains. Identified by the disappearance of the red supergiant. Pair instability supernova. These occur in stars around 150 to 250 solar masses with low metallicity. Keep in mind, the higher the metallicity, the more likely the star is to go supernova at a lower thing. So in other words, high metallicity stars will never get up to these. They're probably never going to go much over about 60, I think. And this also can occur with population 3 stars, which of course got 0 metallicity. And in fact, this will be one of the principal ways that population 3 stars will go supernova. They'll never go core collapse. Typically the population 3, the calculated size of population 3 stars is up around 250 solar masses and greater. There was some suggestion a few years ago that stars that big couldn't be created, but they've now identified some stars that are actually much bigger than that again. Okay, what happens in these, gamma rays coming out of the core from the reaction collide with a nuclei further out in the star and produce electrons and positrons. This reduces the radiation pressure, causing a partial collapse. So it doesn't go through the same thing. This runs away and the star explodes. With a pair instability supernova, the star is blown away completely and leaves no remnant. So there's no black hole in the middle in this one. So it all goes out into the planetary nebula. This can produce as much as 40 solar masses of nickel 56. This is a good producer of iron. Lang Hancock would be happy. Photodisintegration, hypernova. I might add that these as I said, these other types, there's relatively few examples. A lot of this has come from models and predictions, but there have been a few examples that do allow them to refine their models. Stars with greater than 250 solar masses. The nuclei absorbs high energy gamma rays and knock out one or more neutrons, protons or alpha particles. This causes cooling of the core and loss of pressure. The core collapses, producing a black hole. And it will produce relativistic jets carrying away quite a bit of the mass. A quark nova. This is a hypothetical violent explosion resulting from the conversion of a neutron star into a quark star. What a quark star is what a neutron star essentially contains neutrons. It does contain a few other things, but essentially protons and neutrons are made of up and down quarks. You will, in a neutron star, you will get some free quarks occurring, but in a quark star, you also get strange quarks occurring. And strange quarks are a higher level quark, a lot more similar to a down quark, but a lot more energy. Quark stars tend to be much more dense. There have been a few examples of things that appear to be neutron stars but appear to be too dense to be neutron stars, and I believe them to be quark stars, but I don't think anyone's going to be close enough to actually have a good look at them. So, proposed to occur when a neutron star spins down. This is predicted to be a source of gamma ray bursts. There are a couple of different sources, but this is one of the predicted ones. Kilonova occurs in a compact binary system when two neutron stars collide and form a black hole. We've seen the diagram before, no doubt. Produces a short gamma ray burst. Produces a flash more intense than a nova but less than a supernova. Most of the heaviest elements in the universe are believed to be produced in a kilonova. Okay, this is an interesting one here. This is a little plot of everything that LIGO has found up until up until September this year. The Americans have got their funny dates, haven't they? So, or is it that? No, maybe February, 9th of February. So I don't know if you can see all the detail there, but these yellow things here are neutron stars. The orange things here are where two neutron stars have collided to form something. Where it's white there, we're not sure whether the product is a neutron star or a black hole. The purple ones are black holes. The blue ones here are where two black holes have collided to form another black hole. This one here is probably a neutron star colliding with a black hole to form a slightly bigger black hole. But this one up the top here is an interesting one because it's a collision between two black holes of 85 and 66 solar masses. The predicted upper limit for black holes to be produced in supernova is considered to be 60 solar masses. the question with this is, have these two, so each of these two black holes been through a previous merger? In other words, was it four black holes circulating around each other? Yeah. So anyway, so that remains an open question. I haven't seen any more on that one, but that's interesting. Certainly 66 is probably not too bad, but 85 is quite high. That was not expected at all. And that's the one there I was talking about. And you see, all the others are all in fact, the heaviest product, the heaviest component is this one here, which is around about 50. Other than that one I was talking about. It's my Supernovae.
Well, that could be called the beginning.
Beginning in there, yeah. All right, any questions? If I raffled you in. Yep.
What would be the typical composition of a white dwarf?
It's basically got hydrogen, helium, and probably a bit of carbon in as well. Yeah. Essentially, it's formed from this star that really is still quite. Keep in mind that when a star burns out, it's actually the core that's the problem. Unless it spells off all its outer layers, it's still got a lot of hydrogen on the outside. So unless for some reason it's actually got stripped by something, it's going to have quite a bit of hydrogen. It's going to have a bit of helium, and certainly, it's probably almost certainly going to have carbon. Stars that are small enough not to burn helium, which will probably be down in the red dwarf stage, none of those have got to the end of their life. All the red dwarfs are still chugging away on the main sequence. They haven't reached the end of their life, and they won't do so for billions of years.
So are we talking roughly 80 or 90% hydrogen and helium and maybe 10% carbon, or would it be less than that?
Carbon is probably going to be fairly small. There's probably going to be a bit more helium in them than whether it's 50-50 or a bit less, I'm not sure. Yeah. And it's going to vary. It's going to vary with each white dwarf, I would imagine as well. Yeah.
When stars, any star for that matter, has gone supernova, you talk about the elements.
Yep.
Being dispersed as such. Are the elements purely at the atomic level, or they could be big chunks of iron or other metals as such coming out there as well? So when you're looking at a photo like that, you wouldn't want to be flying through it. If it's gas, say, or just
you'd find in fact that's quite a large object, and the actual density of the object is going to be it's probably less dense than a typical atmospheric cloud. Yeah. But I would imagine that there'd be individual atoms. I'm not sure. Whether any molecules actually form at that stage or not. But keep in mind that in a star, everything is all the elements in a star are ions. The temperatures required to burn any of those things to go from even from hydrogen to helium, millions of degrees, and the electrons get boiled off at thousands of degrees.
So it's all at the atomic level then anyway.
It's all ionic, and it's only after it cools down to quite a reasonable temperature the electrons can recombine. Otherwise, it's plasma. So it's not going to form. It's not going to form chemicals until it's cooled.
So how many of the different types of supernova have occurred within the Milky Way itself?
I'm not sure actually, no.
Are they mainly the type 2s and the 1As?
I would say so, yeah. I'm not aware of any of the really big ones having occurred close. Keep in mind the really big ones tend to be ones that are formed in regions that are very, very low metallicity. And I guess we seem to be in a relatively mature environment, which I don't know whether all the stars in the Milky Way are a population 1 or whether some are population 2. I don't think there's any population 3 stars in the Milky Way. I think they tend to be out at sort of billions of light years, way back in time when they were the predominant star. Obviously, you know, when the first stars occurred, they were all population 3 stars. That was the only thing. That's the only thing that can form out of just a pure mixture of hydrogen and helium.
Are there any candidates that we'd be looking at the moment for an upcoming supernova?
BC to Corona to name too. Anything that's a red giant has got the ability to go supernova. I guess one of the things is that, in fact, some of the very big red giants can go through something like 50 or 100 cycles before they go supernova. So if it goes through a cycle, you don't know whether the end result of that cycle is going to be a big bang or whether it's just going to go back into another cycle. Yeah, and the thing that triggers it is right in the middle. So looking at the outside doesn't tell you a lot. I guess when it's contracting, that's the time. That's a sign that it may be heading that way. But as I said, it may just bounce back out again and restart again. Yeah. But certainly all the big super giants potentially will go sooner or later, unless they do one of the other tricky ones where they. Actually, I've heard of Edgecorreno. There's some suggest that may actually go supernova. That may actually just finish off blowing off most of its material and not actually go supernova. So, but I don't know whether everyone agrees with that or not. A lot of people say that's about to go supernova, and other people say that maybe it'll just continue blowing off its material. So I guess it remains to be seen, doesn't it? But certainly it's had about 200 years ago, I think, had quite a large ejection of material, and it was a lot brighter. The star was a lot brighter before that, and obviously it's improved the nebula itself, but the star is not as bright as it was.
I think also it was the brightest star in the sky, wasn't it? Going back about 150 years ago.
Possibly, yeah. I mean, Betelgeuse was brighter than Rigel back at the time of the Greeks, wasn't it? So it was called Alpha for that reason. In fact, there's three stars called Alpha that are not the brightest in the constellation. I can't remember what the other two are now, but that suggests that they're red giants and going through ups and downs. The red giants do.
Any last question?
And they might already be gone. We don't know.
Well, that's the other thing too. Yeah, we're talking about how we see them. Yes, as I said, the further things are away. We
give it a delay.
We can't know. Can't know if anything is blown up faster than the speed of light.
Yeah. Okay, well with that, I'd like to thank Ross. Our final talk before Christmas.
Yep.
Okay, well, good to see everyone back at the Briars for a change after the last, feels like 20 years, but probably not quite that long. So, I think the last time I did this here, apart from that little dodgy one in the middle of the year, was back in about February. So, flash forward to December 2020. Couple of things happening this month. I've included the first part of January as well, since the next meeting's in January. And on the 17th, which is tonight, which is a bit unfortunate with all the cloud, you've actually got Jupiter and Saturn fairly close together with a sliver of moon forming a bit of a triangle at the moment. So maybe we can have a look when we finish up here and see how we go. Comet 88P Hal is the Gamma Capricorn. It's heading out of the solar system, heading out about now to around about 11th magnitude. So you need to know where you're looking, and you need a fairly good telescope. Summer solstice, longest day on the 21st to the 12th. And just for the newer members, you'll notice Mercury in superior conjunction there. That basically means both Mercury and Venus had two conjunctions. They don't have an opposition because they're closer to the Sun than we are. Their inferior conjunction occurs when they're between the Earth and the Sun, and their superior conjunction is when they're on the other side of the Sun from the Earth. And so being in superior conjunction, you need to be a total optimist to think you're going to see it at all. First quarter moon occurring on the 22nd, but I guess the big one, I've actually got the date wrong there. It's supposed to be the 21st, the Jupiter-Saturn conjunction, and they'll be about 0.1 of a degree apart. So if you hold your arm out at arm's length, the width of your thumb is about half a degree. So it's about 1/5 the width of your thumb apart, so fairly close. It's an event that only happens every 18 to 20 years. So for those of you that are 30, 40, 50, you can probably expect to see the next one. For those of us at 60, we've all got our fingers crossed. Full moon on the 30th. And moving into January, probably no interesting thing there is the quadrangent meteor shower from the end of December into about the middle of January. Been highlighting the meteor showers and seem to be gathering a bit of attention lately. Moving on to the next slide, December sky looking to the south, which that way. We can see there's a few interesting objects up there, and once I don't have to try and describe them verbally, I can point them out. One that Ross actually mentioned was the Victoria Nebula down here, just above the Southern Cross. So it's a fairly obvious nebula, one that's quite easy to get for those that are interested. Once again, 47 Tucano there, a good alternative to Omega Centauri as a globular cluster. It's quite a good one to also get, and in my opinion, almost just as good as Omega Centauri. Here you got the Tarantula Nebula. The interesting thing with that nebula is it's in the Large Magellanic Cloud, so it's not even a nebula in our own galaxy. It's a nebula in another galaxy, and it's not a bad one for the astrophotographers to have a crack at. As for anything else, you can just see Orion peeking out the top there. It does come into view with the next slide, and obviously bringing the Orion Nebula in the sword. But we'll go to the next slide. And this is the December night sky looking to the north, that way. And we notice that finally Orion has returned to our night skies, bringing with it its nebula there. But you've got the belt of Orion, you've got Mintaka, Alnilam and Alnitak, and just to this side of them are two nebulas, the Horsehead Nebula and the Flame Nebula. Now, I was discussing this with Greg, who was telling me to see it in the telescope you need a rather special filter, but a camera, if you get it all set up right, will actually take a picture of those two nebulas. I almost got it myself last year, so I'm kind of waiting for that one myself. Other interesting things, particularly from my own personal point of view, is down here, the Andromeda Galaxy. in Andromeda, obviously. It's a fairly large spiral galaxy close to Milky Way. It's part of our local cluster. It's fairly low on the northern horizon, so I don't like our chances from here. But if you happen to go somewhere that's got a decent northern horizon, might be worth having a look for. Okay, so the planets. Mercury is currently a morning object. It's past its inferior conjunction, so once they go through that and Venus go through their inferior conjunction, they pop up in the morning as morning stars, if you like, and heads to its superior conjunction on the 20th of the 12th, so 3 days' time. So Mercury's probably not one you're going to have a look at it in the immediate future. Does move fairly quickly though. Through January, we'll actually return to the evening sky. Venus, still a morning object. In a brightening sky, it is actually starting to go past the sun. We're actually looking at it across the sun at the moment. Gives us a little bit more face, but it's a lot further away, so not quite as big or visible as normal. The Earth is moving towards the southern hemisphere summer. That basically means the North Pole tilted towards the sun. It's also the time of the year when we're approaching perihelion. So generally explains why southern summers are a little bit hotter than northern ones. We're a little bit closer to the sun. Mars, obviously the best one to have a look at the moment. They're still fairly high in the sky. Obvious red disk. In Pisces, for those who want to be technical, that has passed opposition. So essentially, it's not running away from us, we're running away from it. We go a little quicker. So probably the next 2 months or so is the last good look you'll be able to have for another 2 years. Jupiter and Saturn, I'll do those two together because they happen to be pretty much together at the moment. Now, when you think about Jupiter's orbit is not quite as far away as Saturn. Saturn's about twice as far as Jupiter. This is from the Sun. But they are aligning. But don't fear, the Titans are not going to get out of it. So on the 21st, they're going to be about 0.1 of a degree apart. So arm's length, that's probably about a mil or so, 2 mils. So it should be very specky. Hopefully the clouds stay away. And as Peter said earlier, the Society does have a viewing opportunity at the base of Oliver's Hill in Frankston. It only occurs every 18 to 20 years. And the reason for that is Jupiter's got to run around the Sun again and then catch Saturn. It takes between about 20 years to do it. Uranus, still in Aries, will be until 2024. It fair dawdles around the Sun, not in any hurry at all. It has passed opposition, not that that makes much difference to what you'll see. Looking at Uranus even through a decent sized telescope, you're lucky to see a blue-green disk. It doesn't have a lot of features. And yet it's quite specky. You get up close and see that. They found it has probably the second best ring system in the solar system, but you just won't see it through our telescopes. Neptune in Aquarius also passed opposition, but with an 8-inch telescope, probably about all you'll see will be a blue dot, but you can see that it's blue. The appearance of the planets, I really don't know why they bothered to put Mercury up there. As I said, it's on the other side of the Sun at the moment. So I guess if you've got some sort of way of peeking over the Sun, that's what it looks like. Venus, it's gone past its maximum elongation. Maximum elongation is its maximum angle off from the Sun as it heads around the back of the Sun again. So it is showing a little bit more face. It will appear as well, gibbous form, because it has a fair bit of face showing. Is a little bit smaller though than when it's closer to us. Mars, Still an evening object, still quite visible and still quite good viewing position. Saturn and Jupiter, whenever they're up, they're always specky, and you should be able to get them with one telescope, one eyepiece at the moment. Uranus, as I said, not much more than a blue-green dot, and Neptune, they must have been fairly big telescopes when they put those up there, because mine really only shows it as a dot. Other stuff, Comet 88P Howe is in Capricorn till late December. It then moves into Aquarius. It is moving away from the Sun, and will go from 10th to 11th magnitude. So, once again, you need to know where you're looking in Aquarius, and you need a fairly sizable telescope. Comet P 209 Q4 Botini is predicted to brighten to 12th magnitude. Wow. Almost as bright as the previous one that's heading outwards. Alright, it reaches perihelion at about 1.4 astronomical units. An astronomical unit being defined as the average distance of Earth to the Sun. So about 1.5 times is when it starts to swing back to head back to where it came from. Should be visible for most of the night in Eridanus. And meteor showers acting from the 4th to the 17th. So this is the last night really, unfortunately. There you have a bit of a look. There's the Geminis, which apparently tend to put on a fairly good display. And last thing here, these are the minor planets or dwarf planets, members of the asteroid belt that are in opposition this month, and the constellations they're in. So you can see a couple of them in Orion, a couple in Taurus. So given those two constellations are fairly easy to find, you might be able to have a bit of a look for them. Although I would suggest they're probably more one for the astrophotographers to try and capture against the star background. So a couple of shots over a couple of nights and see which one moves. All right. So you've got 7 there. Quite a few this month reaching their opposition, and once again their magnitudes are not that great, so as I said, probably astrophotography would be the ideal one there. Pluto's in Sagittarius, been there for a while, sits around about 9 PM, moving into conjunction with the Sun on the 14th of the 1st. Not that that's really going to make much difference. Alright, you look out there in Sagittarius, galactic centre, and all you can see is stars. So if you tell me which one's Pluto, you do better than I can. And last of all is continuing my solar system tour for those who've waited with bated breath every month to find out a little bit about the solar system. Tonight we're going to have a look at the planet that butted a few jokes and sort of puts a snigger on everyone's face when you mention it. Yes, pun intended, thanks Anders. Uranus, named for the Greek god of the sky. Well, there's a rumour in a cartoon that it wanted to be called Doug, wasn't it? Can't blame it. Consists largely of hydrogen, helium gas, but also contains large amounts of water, ammonia and methane ices. Because it's so cold out there, they exist as ice within the atmosphere. And so they refer to both Uranus and Neptune as the ice giants. Both of them pretty much contain the same sort of things. Diameter, it doesn't really mean a lot as you're looking at the others, but it's bigger than Earth, about 4 times the size of Earth. And currently has 27 moons, but I think all the gas giants are having a bit of a competition to see which ones can capture the most asteroids. Distance from the Sun, well that's one hell of a big figure. So probably doesn't mean much to anyone. So I personally prefer to look at astronomical units. The Earth is 1 astronomical unit from the Sun. So Uranus is 19 times as far from the Sun as what we are. So you imagine it must be pretty cold out there. Orbital period 84 years. Is anyone who's 84 here? Hasn't even gone around the Sun once in any of our lifetime. I'll accept maybe friends.
What do you say?
Very good. As for all planets further from the Sun, best viewed with an opposition, although it's debatable because it's a fair way out, so it's not going to get much bigger or much smaller over a fair arc of the sky. It is up at the moment, and it doesn't have very much detail. Once again, though, 19 astronomical units away, it's smaller than Jupiter, and Jupiter's only about 4.5 astronomical units from the Sun, so it gives you an idea of just how far out we're starting to look when we're looking at something like Uranus. Main unusual thing about Uranus is that actually it's tilted over in excess of 90 degrees, so virtually rolls around its orbit on its side. And as I mentioned earlier, it also has well, all the gas giants have ring systems. It's just Saturn's a lot more visible. And that's a picture of Uranus. That could just be a blue ball that I stuck up there, and you wouldn't know, would you? There's really not much to be seen when you look at it. All you can do is just say, have a look at it and say, I'll see Uranus. Okay? So that's about it. And that photo was taken by Voyager 2 and is on here courtesy of NASA. So if that's the best Voyager 2 can get going past the thing, you're not going to see much more of the telescope.
Take your telescope back.
Righto, tonight's information was provided by Astronomy 2020, Wallace Dawson Northfield. I think there's some 2021 ones available for those that are interested. Certainly a lot more information than what I'm presenting here. I'm just sort of skimming through the interesting and exciting stuff. And as I said, Uranus image courtesy of NASA, picked it up by Voyager 2. Any questions?
I'm going to say the smallest moons around Jupiter are around 1 kilometre in diameter. The smallest around Saturn are actually 0.5 kilometre. But the smallest they know of around Uranus and Neptune are up around 10 or 20 kilometres, which suggests there's some that they haven't found yet. They just haven't been
I think Voyager went past pretty quickly, so
they
I
went
think
pretty
really have a good look.
quickly, yeah. It's pretty hard to see it even with the best telescopes.
Yeah.
Pretty old telescope on the Voyager.
Yeah, I put the telescope to bead on Uranus one night, but there was nothing else. Jupiter and Saturn weren't up. And everyone was pretty happy, all the public members were happy, oh, that's Uranus. Except the kids, I said, that's Uranus. Thanks, kids.
Okay, let's continue on. And we've already had Sky for the Month by Mark. The next one is something put together by Sky, all on the subject of 12, goes for about 5 minutes or so. And I'll go through the Hyabusa returns, so there's 3 short features on that one, and also showing when it actually re-entered over Woomera as well. Then we'll go through the SpaceX launch, which goes for about 8 minutes from it lifting off to when it came back down in a fiery ball.
Solar eclipse in Chile.
Then we'll look at the total eclipse in Chile and Argentina that was 2 days ago. In fact, they showed it on the TV news earlier today.
I think, yeah, they did, yeah.
And lastly, explain why glass is transparent before closing.
Hi everyone. There's a story how a title like this came to be. But we'll reach that by tracing things back to front. For now, I have another one of those. All my life, I have not known for sure why eggs are sold in dozens. Do you? Why do we have a unit of 12? Did some kings have 12 fingers? Here's an eclectic mixture of observations. But please don't believe these or anything without verifying for yourself. The word dozen is from French douze for 12 and douzaine for dozen. Examples that show usage but not necessarily how 12 came about are 12 pence in a shilling. A long time ago, 12 inches in a foot, 12 music notes on a chromatic scale, 12 and 24 hours, and 12 months. Amazingly, December came from Latin decem, meaning 10, from the old Roman system of 10 months in a year. Highly interesting are more observations. 12 is a very useful integer for ratios because it can be divided by 1, 2, 3, and 4. Here I leave you homework to find out something related. What's the significance of the number 362880 relating to its divisibility? Now remember the magic right-angled triangle. The sides are 3, 4, and 5 in any unit. And 5 squared equals 3 squared plus 4 squared. Now 3, 4, and 5 add up to make what? 12. And 4 by 3 is somewhat an obvious rectangle to make anything, like a baking tray. 4 by 3 is 12. In fact, 4 by 3 has been the aspect ratio of many things, like the screen of traditional TVs, movies, cameras, and photo prints. Of note is even the modern pixels 1024 by 768 is a 4 by 3 ratio. Another day I might go into how electronics created the binary system for computing. So instead of base 10 in the decimal system, we have base 2 using the notation of 0 and 1, and the hexadecimal system of base 16 using the notation of 0 to F. But, I need to state here, in case I die tomorrow, that had I worked further in digital electronics and computing, it might, as it should have, progressed to tri-states. Just imagine that. The world, the natural world, is analog mainly. It's natural when digitized to have 3 states in everything. And computing power would have been even more amazing. Now back to 12. I hope you will discover, if not already, some extremely fascinating information about Mesopotamia. But please note that other ancient cultures may have valid claims too. This is apparently a Greek word. See, you can read this Greek word. Unlike English, which is not phonetic, and the vowel A can be pronounced any of about 6 ways, so English borrows and mispronounces a lot of things. This in Greek apparently is pronounced something like Mesopotamia. The Mesopotamians, including the Babylonians, were awesome engineers, mathematicians, and astronomers. They gave the world the wheel, irrigation, writing, sail, math, the famous Nimrod lens, and astronomy, including the zodiac. The Mesopotamians had 12 lunar months of 30 days each, plus 5 days holidays to tally as 365 days for the sun's seasonal cycle. There, 360. The crux, 360, is very handy for ratios, being divisible by 1, 2, 3, 4, 5, 6, 8, 10, and 12. Oh man, massive fun! 360 degrees for a circle. So the longitudes, and plus and minus 180 degrees for latitudes. Cut a pizza into 4 quarters. Cut each quarter into 3, and you feed 12 people a slice each, and have just made yourself angles of 30, 60, 90 degrees, etc. 12 hours daytime and 12 hours nighttime. Each hour 60 minutes, each minute 60 seconds. There, 360 appears again in 3600. Also, these 12 apparently was counted by using a thumb to count out the bone sections of the 4 fingers. As a base 12, the duodecimal system, if you use each digit of the other hand, you can count out to 60. So 12 it is, for this month being the 12th month just by convention. We are not asking our members to give. We are inviting you to take 12 spots over the next 12 months for 12 lucky, plucky, ordinary ones of us. Give away for free 12 chances to play. Play being a presenter for 10 minutes. Free support. Choose any fellow members to give you peer support. I certainly will be on standby for your own style, which can be formal or casual. Now, what topic? Oh, that part is the easiest of all. The topic hardly matters, as long as it has something to do with science, STEM in particular, including astronomy, and as long as it is useful for the audience. Some examples you can brainstorm with friends are: adopt a star, adopt an object to be your subject. I'd be rapt if you do a show and tell of something practical. By the way, any music submission audio or video, will be absolutely smashingly treasured. A note on professionalism, not only reflecting on each of us. MPAS materials, written or verbal, are shown publicly, and some standards are science-based. Credit the sources, socially appropriate, and time limit, 10 minutes in general. In fact, I am super delighted to say one spot is likely taken already by a very awesome 7 years old who will speak on my behalf. Let's see. Now I shall await your email to say yes, like right now. Happy holidays! May your star shine bright. Bye!
Here's a picture from Woomera on the right-hand side of them extracting the capsule from Hyabusa 2. As you see, it's about 40 centimetres across. And why the guy is dressed up like a bomb disposal person is because indeed there were charges in there that were spare for just in case the parachute didn't release properly on the way down. So they had to disarm it when it came to the ground, so that's why he's in all this gear. Shown over here on the left, they opened the capsule today in Japan, so it was flown back to Japan, and you can see the sample of asteroid Ryugu down there on the side. I believe there are two samples. One was taken from an initial touchdown, and another one was taken after they fired a projectile into the asteroid and blew the material up. So this is from the initial touchdown one, and I don't think they've done the other one yet. They had to open it up actually inside a vacuum chamber, so they're trying to keep it as quarantined away from Earth as possible. And so if on the news in the next couple of weeks you hear that Godzilla is running rampage in Tokyo, you know where it's come from.
I find that puzzling, Peter, because I couldn't believe, and I've heard it a couple of times on the news, they came back with 1 gram of dust. Now that obviously looked more than 1 gram.
That's a lot more than 1 gram, yeah.
And
that's a lot more than 1 gram. No.
All that for 1 gram, I wouldn't have thought they'd get enough.
I think 1 gram was probably their aspiration of lowest range before you call it success, and that clearly is a lot more than 1 gram that's in there. They were lucky in that regard. The source of this video was JAXA, which is the Aerospace Agency. going to land.
Japan's Hyabusa 2 spacecraft is set to make history this weekend when it returns the first subsurface asteroid samples to Earth. And as if the milestone isn't exciting enough, it gets better because the sample capsule is set to land right here in Australia. To tell us more, Professor Masaki Fujimoto from the Japan Aerospace Exploration Agency, JAXA, joins me now from Woomera. Good morning and welcome to News Breakfast. Can you tell me, why is the sample going to land in Australia?
Oh, because Woomera has a big flat open space which you need for safe landing, and it's really accessible. And in Woomera we have people who share the same values with us, and they are really helping us out. So these three elements that was necessary to make the smooth operation of capsule recovery.
Now, are the locals around Woomera going to be treated to a fireball in the sky?
Yes, Kuba Pedi, 400 kilometers north of Woomera, that's the best spot to watch the spectacular fireball running across the sky. It's going to be around 4 a.m. in the morning of December 6th.
Right, so that's in the very early hours of Sunday. Now, what is it that's actually landing near Woomera?
Oh, it's a sample return capsule. Its size is like 40 centimeter diameter, and it contains samples we acquired from the surface of Ryugu, one of the primordial asteroids. By analyzing that sample, we think we can learn the process that made our planet habitable. After releasing the capsule, it's gonna have another strategic correction maneuver and then go back to the interplanetary space. And it's gonna have to cruise for another 10 years, but after 10 years from now, it's gonna rendezvous with another asteroid. A very small asteroid, but that's on an orbit that may hit Earth someday. So Hyabusa 2 will have a new mission related to planetary defense.
I am so glad that JAXA is on the job and that Australia's getting to help out as well. Professor Masaki Fujimoto, thank you so much for joining us on News Breakfast and best of luck for this weekend.
Thank you very much.
Now you'll see the actual re-entry footage that was captured from the rocket.
It's really exciting.
This was also recently. This is the big one intended for going to Mars.
10, 8, 7.
Nobody was on board, by the way.
5, 4,
Who told you that?
2, 1, 0.
Compare it to a Saturn V, how there's a massive flame behind it. So you see the two cameras over on the right as well, actually looking down from inside, so you can see the rocket motors there gimbling every now and again to correct the attitude of it.
Yeah, that was planned.
So they said.
Changing gears.
Just about run out of puff.
Well, to get the speed up, so. Go too fast, we'll come back.
Just a little bit.
If it's clear, just
bang on target though.
Yeah, probably should have lit the rockets a bit earlier.
And was it that dust? There's a pressure issue in their return propellant tank.
Oh, was it?
Yeah, not enough pressure after the ascent.
Someone was saying that it also the rockets, one of the engines might have started deteriorating from inside because of the green flame that they started shooting out at the end is indicative that it was burning copper from the fuel lines and that sort of thing. And that's what might have caused them to lose thrust as well.
I really don't want to lose this, and I can easily see that there are some clouds in front of the solar disk, my friends. But anyway, let's go. Look how dark is the environment, because it will be night for a while. Not completely dark, but dark enough, and this is one of the most unique feelings you can experiment during totality. And likely you will see the diamond green when we will be seconds from the totality. That is when the solar disk will be perfectly, the lunar disk will be perfectly in front of the solar disk. Perfect alignment. I'm very, very excited. They say 2 minutes 20. From Puchon in Chile. And it's incredible to see how all these, the upcoming totality is affecting so strong the residual light all around. Keep in mind, this is in the center of the.
How many here have experienced a total solar eclipse?
Over the States,
Okay, about half.
That's in Spanish, that's the sun. Total eclipse of the sun, that's Spanish.
And here we are, my friends. Unfortunately, the sky is not perfect, but the motion is incredibly strong.
Speak Spanish.
We are fully approaching, you see the
I
totality.
used to be
Not
able
sure
to
what
speak
we
it
see.
well, but I don't know
It depends
anything else.
on the effects of the
I can read
residual
it though,
cloud.
I'm a better translator than interpreter.
Our friends are facing a few clouds, and let's see what the camera can do under these not ideal conditions. But we are
So the last thin strip of the sun will disappear, and then it'll break up into like little beads known as bathing seeds.
Street lamps on. Look, my friends. Oh my God, this is amazing. And we should see the corona. Here it is, my friends. Totality is here from Chile. Magic, the solar corona. This amazing feature we can see just during the totality, when the moon is blocking the light coming from the solar disk. How amazing, my friends. Let's hope really we will see this again from other places. How beautiful it is, my friends, to look at this. Look on the left, the residual solar wind is going, and you can see grains, and then the totality. And at this very moment, we have to change dramatically the setup. Oh my God, this is super, my friends. This is super. You can see prominences, and you can see so well the corona. This is the long-awaited totality, from Chile, and I'm truly, I mean, I cannot tell you my feeling right now because this is super, this is amazing, this is unique, this is precious. And I want to thank our friends in Chile for making it possible for us to bring this to our audience as well, and to the many friends connected to SpyDis. This is super. I cannot say you how what I feel here. My English is not enough to express my emotion in the most genuine and complete way. This is me. Nothing to say. Just look and enjoy in silence. Perhaps better. This is amazing. Truly amazing.
Yes.
The totality will last a handful of seconds more than 2 minutes, and we will lose the corona and the provinces. And then
you'll surely see the diamond ring as the sun starts to come out the other side.
How beautiful it was. Breathtaking. Outstanding. You can see on the right where we had the first view on the totality. It is now gone. How beautiful, friends. These have been amazing.
It's the diamond ring on the left.
And we are done. The diamond ring just telling us totality is over. I am just keeping my breath.
Now they've cut over to the view from Argentina. So the shadows moved across in that period of time across South America, and now you're seeing it from the eastern side.
Updating, but as I was expecting, they switched to another telescope. At least the one on the bottom left is sharing live images. I cannot imagine how hard it is for them to handle this task. How beautiful. You see, they increased the exposure time. Oh, my friends, look at the bottom left. The diamond ring, and then the corona is showing. Oh, through the cloud, but amazing, my friends. Amazing, my friends. Wow, we see the totality again, this time from Argentina. I'm amazed by this. I cannot tell you by words the feeling while facing something beautiful, so beautiful, so beautiful. How amazing, my friends. Even if with clouds, we are still enjoying the totality. For another time, we add this special site from Chile, now from Argentina, taking benefits from our spheric planet Earth. And I'm truly amazed by this. How beautiful. And a couple of minutes, I think 50% is gone. Look, my friends, even with clouds, we are truly enjoying this. The colors, you can see how beautiful. it is ending because you see on the upper
Too
right,
different from the solar eclipse that was
you expect to see
here in Victoria in 1976 through
sun
cloud.
coming back with the diamond ring. There are different clouds.
What's this?
They are very likely playing a bit with the camera settings to find a workaround against the cloud because it is very difficult. They are doing a good job, by the way. Now, Peurto is saying bye, friends. See you next time. Wow, my friends. Speechless.
Yeah.
And then now have the filter back. And we will see the lunar disk leaving.
What I'd like to explain over the next few minutes or so is why some materials are transparent and others are completely opaque, why light can get through some materials, why light can't get through other materials. In particular, glass. What makes glass transparent? Why can light get through this? Yeah, so what is going on is with glass compared to other materials, the important thing is how the atoms are arranged in the solid. And how the atoms are arranged dictates, and this is the really important bit, how the electrons are arranged. And it's how those electrons stack up in different energy levels, or the energies of those electrons, that dictates whether light can get through. Right, so what I'm going to do now is I'm going to pretend to be a photon. I'm going to move through this room, and this room represents a substance, lots of atoms, electrons dotted around everywhere. So I'm moving through with a certain amount of energy. And my job as a photon is actually to take one of these electrons from its ground state, its lowest energy state, move it up and bring it up to a higher energy level. And when I do that, basically my job is done and I'm absorbed and I don't make it through the solid. So if it's brick, for example, this is what happens. The photon comes through, it takes an electron from the ground state, moves it to a higher energy level, is absorbed, doesn't make it through. The substance is opaque. For glass and other special materials which are transparent, instead of what happens is that the difference in energy between the ground state and the high energy level, which we call the energy gap, is much too large. And as a photon, I'm coming through, and what I need to do, or to be absorbed, what I need to do is actually take one of these electrons and bring it all the way up here to this excited energy level. But I don't have enough energy to do that. I simply can't get it up there. So therefore I'm not absorbed and I pass through the material, getting out the other side, and so the material then appears transparent. So the energy difference between the ground state and this level, the difference between those two we call an energy gap. And an electron can only either be here or here. It cannot exist in between. We cannot excite it there. So the photon gives up that energy and transfers it there, and then it's the photon basically is dead. So when it comes to glass and diamond and other transparent materials, that energy gap between the ground state and that excited level is so large that photons of visible light, photons with visible wavelengths, photons that we can see, have not got enough energy to actually get it from here all the way up there. Right, so now we're going to go down the lab and we're actually going to do an experiment, or look at an experiment that the second year undergraduates do here, which is to look at how light is absorbed in these materials. We have a light source, we have something called a monochromator sometimes is how it's pronounced, and what that does is from the white light source, it selects out a particular wavelength of light, a particular colour of light, a particular energy of light. And so this, at the moment, is telling us that the wavelength of this light is roughly, I haven't done the calibration, so I'm assuming it's right, roughly 525 nanometers. And so I'm going from, at this point, high energy photons with this bluey green colour, up to low energy photons. So what we have here is a sample. Now this is sort of midway between what we've been talking. It's not quite completely opaque, it's not quite completely transparent. You can see it's coloured, it's orange. It's an example of something called a semiconductor. What's interesting about this semiconductor is that that energy gap falls in the visible range. It means that some photons of light in the visible have enough energy to excite those electrons, whereas others don't. And we can actually measure that transition from where the photons have enough energy to where they don't have enough energy, or alternatively where the photons get blocked because they have enough energy compared to where they actually get transmitted the whole way through. So what I'm going to do now is here, it's just the light, just so we could see it, I've put on the side of the box that contains the photodiode. This is actually the active part. So what I'm going to do here, so I'm going to move this across and put it on the photodiode. And now we see light getting through. What I'm going to do is put this sample in there. I'm going to put it in front of the photodiode. So the light is coming through from here, through here, through here, through here, going through the sample now and ending up on the photodiode. And you can see that we've got 0. And the reason we've got 0 light coming through now is that all the photons are absorbed, because photons of this energy have enough energy to promote electrons, to excite electrons across that gap, so they're absorbed, so they don't get through. When we change the energy, so we're going from the blue to the red, the dial will start to come up, because at that point the light is now getting through, because at this point the photons no longer have enough energy to actually get through the sample, because they're not promoting those electrons from the ground state to the excited level.
And lastly, over about 2 minutes, we'll compress in the entire history of the universe in the next 2 to 3 minutes. And the background to that is by Diana Clark, who sent in a piece called Dust from a Million Stars, which obviously is some relevance to tonight's theme, and done a cappella, which means no music as such.
Dust from a million stars, dust from a million stars, is who we are, is what we are. Dust from a million stars, dust from a million stars, is who we are, is what we are. Dust from a million stars, dust from a million stars, is who we are, is what we are. Dust from a million stars.
And we'll see those of you who are coming to the dinner on Saturday night. We'll see you on Saturday night. Otherwise, we'll see the others in the new year.
Adios.
Okay. Bye, everyone.